How are craters formed on the Moon? The Moon can't hold together enough particles to form a significant atmosphere around it, because it does not have the gravity that planets have. Its atmosphere, if you can call it that, definitely isn't anything like what we know from other celestial bodies in our solar system, including our very own home, Earth. Most particles around the Moon, even those that move at a relatively low escape velocity, manage to escape its very weak gravitational pull. The negligible amount of particles that don't and that remain surrounding it, doesn't amount to a dense atmosphere. Earth, as a contrary example, has a very dense and rich atmosphere. It is made up of oxygen, nitrogen, methane, helium, krypton, hydrogen, neon, argon and carbon dioxide. How is this related to the craters on the Moon? Meteorites. While moving through the vacuum of space, meteorites, comets and other space debris, travel at speeds reaching tens of thousands of miles per hour. But when the gravitational pull of a planet or that of a large moon, not like ours, tugs a meteorite inbound, and as it hits the rich atmosphere, the air in front of it compresses immediately. The gases become compressed, and their temperature rises. This causes the meteorite to heat up so much that it glows, reaching temperatures as high as 3,000 degrees Fahrenheit, 1,650 degrees Celsius. The same way they form on Earth minus the burning up in that atmosphere because of friction with air molecules in part. The mass, velocity and acceleration of whatever is impacting and the angle of the impact with the surface determines how much power the impact is and how big and what the shape of TES of the craters and ejected material will take. Just like on Earth, craters can be volcanic or caused by impacts. Quote dot. 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 The term impact structure is often used synonymous with impact crater, and sometimes, impact structures are distinguished from impact craters by their weak morphological signature compared with a true crater. In both cases, the conditions of a hypervelocity impact and propagation of shock waves are crucial for the formation of these geologically extraordinary structures. The three stages of impact crater formation in impact research, the subdivision of the crater forming process into three main stages has generally been accepted. These stages are, the contact and compression stage, FIG. 6. The excavation stage, FIG. 7. The modification stage, FIG. 8. In the following, these three stages are illustrated and described in a somewhat simplifying manner. Fig. 6. The contact and compression stage of impact cratering. On impact of a cosmic body, shock waves are starting from the contact point and propagating into both the underground target rocks and into the impactor. Impact shock waves are characterized by an instantaneous onset of extreme pressures up to the order of megabars and extreme temperatures up to 10,000 degrees or more on release of the pressure. These temperatures are enough to more or less completely vaporize the impactor and a volume of the target rocks roughly comparable to the volume of the impactor, resulting in a giant expanding impact vapor plume. On propagating roughly hemispherically into the underground target rocks, shock wave energy diminishes and so do pressures and temperatures. Correspondingly, a zone of rock melt follows the vaporized zone, and when shock energy is further lowered, rocks will only be heavily damaged, fractured, brecciated, with decreasing intensity. Driven by the hypervelocity impact deformation, melted and fractured rocks will be accelerated behind the shock front, initiating, in the second stage, the excavation mass flow. Since impactors can attain to practically arbitrary size, the kinetic energy brought to Earth by impact and turned into geological processes may practically be unlimited. This is clearly different from normal, endogenetic geological processes like volcanism or tectonics, and may contribute to the situation that impact remains inconceivable for many geologists, all the more as this energy is set free in extremely short time. Fig. 7. The excavation stage of impact cratering. Different from the cobble into mud craters, the excavation in impact cratering is inextricably linked with the propagation of the shock waves. Shock waves behave like other waves, they can interfere, and they may be reflected and refracted. Spreading outwards from the point of contact, the compressive shock waves are permanently reflected from the free target surface as tensile rarefaction waves of comparable intensities and, like the shock waves, are propagating downwards. In this way, all rock particles behind the expanding shock front are captured by both the compressive shock and the tensile rarefaction, and both combine into a vector of acceleration. Computing these vectors' direction and magnitude for each point in the subsurface, a field of excavation flow with arcuate trajectories is shown in the sketch above. Fig. 7 will result. This flow field is growing with time, and the rock mass flow is directed upwards, sideward and downwards. In the upper part, the flow field enables the rock masses to escape as ejecta from the growing excavation cavity. Below a trajectory defining floor and walls of the expanding cavity, the rock material cannot leave and is compressed sideward and downwards. The excavation stage ends on release from shock, and when the displacements by excavation cavity formation and downwards sideward compression are maximum. The now existing bowl-shaped structure surrounded by an uplifted rim and a blanket of ejected material is termed the transient crater, obviously indicating a continuation of the impact cratering process arriving in the modification stage. We saw shock wave and rarefaction wave propagation are essential in the formation of a meteorite impact crater. Apart from the distinct role rarefactions waves play in the formation of the excavation flow field, they are especially relevant geologically. A compressive shock pulse is not only reflected at the free target surface but also always when it impinges on a boundary of material with reduced impedance, equals the product of density and sound velocity, where part of the energy is reflected as a rarefaction pulse. The reflected tensile stresses are insofar crucial as the tensile strength of rocks is much lower than the compressive strength. Hence in an impact process much more damage is in general done by the rarefaction waves and not by the compressive shock waves, and many peculiar structural features that are observed in impact structures and that may puzzling geologists are the result of strong tensile forces acting on all scales. Same way craters on the Earth form. Something whacks into the surface of the Moon with incredible force, creating a localized shockwave and an expanding cloud of rock and regolith that shoots out from the point of impact. Eventually this cloud falls back to the ground, creating the distinctive rimmed bowl shape we associate with impact craters. There are a few differences since the shockwave doesn't travel through air, only rock, and the lower gravity means that the cloud of debris can travel further, but the same basic principles are at play. Some distant time in the past there were also likely craters created by seismic activity such as volcanoes, but all current evidence suggests the Moon's interior is too cold and dormant for that to happen anymore. As to why there are so many on the Moon, there are two reasons. The first is that the Moon kind of serves as a celestial Roomba for Earth, sweeping up a lot of debris that enters into our local space and dragging it in before it reaches us. The second is that it doesn't have the thick atmosphere of Earth burning up smaller meteors before they can hit the ground. Anything unpowered that enters a suborbital trajectory on the Moon will hit the surface, and will create a crater when it does so. Good science has an alternative theory. One that matches all the evidence, so for all craters in the solar system there is an alternative explanation. It is based on serious laboratory experiments. These experiments produce every feature known about craters, from flat bottoms, to steep sides, to central peaks, to hexagonal rims, to mini-rim craters to craters with enormous rays. They do not involve mechanical impacts. Yes, you have guessed it, the electrically driven plasma discharge works every time. In a classical setup the negative 10,000 volt probe is suspended above a positive metal plate with dampened, slightly conductive clay representing the planet's surface. The video is impressive, producing a classic round crater because of the rotating Birkeland current filaments that form the cutting edge. 1. What is harder to imagine in our current, boringly safe solar system as any planetary bodies moving close enough to each other to cause these massive lightning strikes? That is one of the unknowns addressed by Eduardo Cardona in his several books. 2. Here's one of the series.